Okay, anybody want to solve some other problem? You? Come.
Let me do exercise 6. The question is we need to prove that every outer planar graph is 3 colorable. So what I remember that it directly follows from the statement that outer planar graphs are 2 degenerate. Okay, since it is 2 degenerate, you can directly greedily color it by its degeneracy order uh, to show that it is 3 chromatic. But you can do it more simply in this manner. Suppose we have, do you know the definition of outer planar graphs, right?
Explain.
Okay. So basically a outer planar graph means a planar graphs whose vertices can be written in a cycle. Okay, or you can say the like this manner. There will be some outer face and all the vertices will lie on the boundary. No vertices are inside. Inside we can have diagonals like that. Okay. In this way, the graph can be. So, okay. So how you are going to do this? Suppose we are considering a minimal counter example. That is an outer planar graph which is not 3 colorable. Okay. So basically how we will do, we will delete these vertices over here, creating a smaller outer planar graph, and now this will be 3 colorable. Okay, and now we bring back these vertices to use the same 3 colors to produce a 3 coloring of the whole graph. So that's a simple idea.
You know what is missing here?
What is missing?
Okay, the outer parameters, you use the same fact, outer lines are to evaluate.
Mm-hmm.
Because you assume here you have vertices of degree 2. Implicitly.
Implicitly.
Can you prove that you have vertices of degree 2? Let's say you teach somebody who has no idea of mathematics, nothing.
Mm-hmm.
So you have to say, okay, outer planar graphs. So if you want to have self-contained proof, how you prove that you have vertices of degree 2? It is the same as to the genericity. You automatically assume you have vertices of degree 1 or vertices of degree 2. And now when you say, you take the last chord, you take the last chord, you have no chords anymore, yes? And if you have some other vertices, must be of degree 2, yes?
Because standing with a triangle, obviously we have a vertex.
Sorry?
Like some triangle.
Oh, that's not the triangle. But prove it you have it. Prove it you have it. So you should go like, you just take, first you draw it on a circle, yes? First you can assume it's two connected. You've said. And if it's not two connected, you take an end block. And you have an end block, let's say. And then you take a chord. You draw it nice, you take a chord. And then you ask, maybe the cut vertex, it's hanging to the graph somewhere, it's here. But then you ask yourself, this is a chord, diagonal. Do we have diagonal in that part? If we have diagonal part, remove it. And let's say we come to the, do we have any more diagonals? No. And this is because this is diagonal, we're going to have something here, some vertex. And if there is no chord, all other vertices here are two vertices. I think this is kind of Again, enter the immediate argument, but okay, little later, yes. So that's true. This is very easy exercise if you assume the graph is to degenerate, or in other words, it contains one or two vertices. Okay. So let's read this exercise also. What about exercise 2? Is something okay or something good?
It's quite easy.
Easy. So doesn't matter, maybe somebody should write it down. Yes? Maybe it's not easy for everybody. Or it is easy for everybody. You want to write something?
We are given a plane graph G and given that alpha plus beta is equal to 3, and we have to prove this, that summation over vertices alpha degree of v minus 6 plus summation over f beta L of f minus 6 is equal to minus 12. We just open the summation, that is and here over LF minus 6 times of faces. So we know that this is twice of edges, that is minus 6v, and this is also twice of E minus 6f. So 2e common, we are given that alpha plus beta is equal to 3 and it is equal to, and it is minus 2, so it comes out to be minus 12. And one special case we have read in disconnected discharging method today itself, where the alpha is equal to 1 and beta is equal to 2. Thank you.
What about how the relay for I equal to how? This is also yes.
Sir, by taking an example, can you show how discharging works on planar graph? A small example also works.
exercise in a way discharging. Yes. Anybody else? Oh. Which one? Huh?
Question number 4, question exercise 4.
Four. Yes. This is also discharging. Yes, something to do with the post discharge.
We need to use discharging for that, sir.
Which one?
Exercise 4.
Yes, in a way.
Just for the handshaking when it follows.
That this is in a way implicitly using discharging. So what? You know what? Now together, yes. So exercise 4?
Sir, exercise 5. It has exactly 2 minus vertices are at least.
Yes, what's question about exercise
Question
5?
5. What graph you should assume for plane graph in order to graph? It has 2 minus vertices adjacent.
Yeah.
Is it at least 2 or exactly
These two minus?
2? EWO 2. 2 minus. It has
At least.
2 minus.
2 minus mean it can be also 1.
Number of those vertices should be exactly 2 or
No, you get 2 vertices which are adjacent like that. It's mean in the graph, in the graph, you may have this vertex of degree 2 and vertex of degree 2. Two vertices may adjacent. So you may have vertex of degree 1 adjacent to vertex of degree 2. These are 2 vertices which are degree 2. This is 2 vertices which are degree 2 minus, yes? Or you can have also 1, if it's very close. Not in the number of games, but there you have 2 adjacent vertices, yes? You have 2 vertices that are adjacent and both are degree 2 minus. Let us move that, okay? It's your turn? Yeah.
Exercise 3. Sorry, 4. Okay, so basically in the exercise 4 we can use result of exercise 3, and if you don't want then I can do separately. What do you want? So we can do separately also. So let's start it. We need to show that planar graph has a 5 minus vertex. Okay. So every planar graph
as 5 minus vertex. Okay. So yeah, we have a Euler formula, that is n plus m. Sorry. N minus, right, n minus m plus f equals to 2. I think it is correct, maybe. Yeah. So, and we know that summation of LF is equals to 2m. Okay. We consider that girth is we know that if G is a cycle, then girth must be greater or equals to 3. Okay, so we can here consider that 3f must be less than or equals to 2m. Okay. Now we put this thing into this formula, in Euler formula. Okay. So here f equals to,
Directly for exercise 3, exercise 3
yeah, I have asked about that. So someone has no, so I have tried to formally prove that thing. Okay. So we have a f is less than or equals to 2m by 3, and we will put this inequality in the Euler formula. We have n minus f equals to equals to what? Yeah, equals to 2 minus f, and we have n minus m is greater or equals to 2 minus 2m by 3. इसको इस तरफ 2m by 3, is it correct? Minus is 2m by 3 minus m greater or equals to 2 minus m, sorry, m mass multiply किया m by 3 greater or equals to, greater नहीं, then तो है यार. So m is less than or equals to, I have made some mistake. Why? Three. Yeah. Now 2m is less than or equals to this thing, n minus 2, and we know that we by handshake lemma 2m equals to v, where v belongs to vertex set of G. Okay, and yeah, and we can also write it then, minimum degree of G into n is less than or equals to degree sum of V, and then it is, yeah, and is less than or equals to 6 minus 2 by n we have. Okay, so since n is greater equals to, we have considered n is greater equals to 2. So delta G must be strictly less than 6. So from here we have strictly less than equals to 5. Is it fine? Or maybe we can do that from maybe that exercise 3 formula. Okay.
5 minus vertex doesn't mean that we have a vertex of charge minus 5, that is degree 1. It doesn't mean that.
5 minus vertex is meaning that G may have a 2 vertex degree, 1 degree vertex, 2, 3 degree vertex, 4 degree vertex. It has. It means.
It doesn't mean that the charge of the vertex is minus 5.
It's not about charge. They have written, what is they have written? Planar graph has 5 minus vertex. Okay, so let's do the second part from the maybe exercise 3 formula. That is n is less than equals to which formula we have? Yeah, G into n minus 2 divided by G minus 2. Here girth G is given to us, that is 4. So from that here multiplying to both sides and G equals to 4 we have, then this, and 2m is less than equals to delta of G into n. कुछ गलत है? Okay. Okay, so from that we have delta of G less than equals to 2 है. Okay, यहाँ पे multiply 2 करना था. Yeah. So that is also 4. Yeah. So 4 into 8 by n we have. Yeah. So from that delta G should be strictly less than 4, and from here delta G should be less than equals to 3. That is what we have to prove. Okay, and maybe third part can easily do that. Okay.
Should I try to solve exercise 7? Anyone want to solve this equation? No?
Exercise 5.
No.
You can give any hint to some.
So exercise 7 now. So just 7. Exercise 5 we solve something more. Okay, let's do 7. So, exercise, what we said? Exercise 7 or 5? 7. Okay. What was Birkhoff diamond? We have two triangles and all these 4 vertices are of degree? No? No. Five, 5. Okay? So this is the core. We make the ring. And additionally, because we assume it is internally 6 edge connected, this ring is a cycle. It doesn't have a something there, I don't know what. The same vertex somewhere, yes. Maybe even if it has, should not be a problem. Yeah. For zero visibility doesn't matter, for D can matter a little bit. So this is the diamond. And these are all vertices of degree 5. So we may extend it. So actually the situation is like this. So we have here, yes, you have here like this, 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 and like this. So this is the ring. This is the ring. So I will use the same notation as it is in the here. 1, 2, 3. Okay, this is I forget to draw one vertex here. Okay, and this is like x1, x2, x3, x4, x5, x6. Can we have like whatever we have colored on the pink properly on the pink ring can extend it inside? Yes, every coloring can be extended. Probably if we little bit play, we will soon find something that cannot be extended. Yes. We use 4 colors. Yes. If let's say we have by mistake colored 1, 2, 3 here. This part of the ring. Then we are forced to have here color 4. One. Now we would like to have here, to force here to be something, some of this, yeah, 1, 2, 3. Okay, so what should we put it here? Maybe you should help me somehow to, what about I have here, two, yes, and okay, and I have here, I would like to force here 4. So I would like to have here 3 on 1 maybe, yes. No, I cannot have here 1. Let's have here 2. And here I have 1. And maybe here I have 3. I'm still forcing here 4. Let's have here 4. Let's have here 3 again. And then I'm forcing here 4. And then I have here 3 or 4. 3 or 4, yes? And then I have to color this 3. 1, 2, 4, I have to color 3. And this 1, 2, 4, I have to color by 3 here. And then I have problem here. Do we agree? So, this means it is not, the Birkhoff diamond is not dereducible, because if by chance I color here 2, 1, 3, 2, 1, 3, because I'm gonna, what is the procedure? I'm gonna take out the diamond, color by induction the rest, and then extend it the coloring side. And imagine when I take out the diamond, the ring I color it in this way. 1, 2, 3, 1, 2, 3. Then 1, 2, 3 force me here 4, 1, 3, 2 force me here 4, 1, 2, 4 force me here 3, 1, 2, 4, 4 force me here 3. Then I will have to put 3, 3, and this is a problem. Okay, so this means Kirchhoff diamond is not dereducible. So what should we do in that case? We hope that it is irreducible. So we will identify some vertices on the ring and then color the graph outside part. And when we go back, identified vertices will get the same color. Let's say I identify these two and then color, and I'm going to have 1, 1 here. And this will not be forced 4. If this is 1, 1, and 3, it will have colors 2 and 4. It will have more freedom. Okay? So, let me do this again. So, another drawing, because this is now very dirty. Yes. So, let's have like this, maybe. This is maybe smaller, yeah. I will explain how I will. Actually, we have this on the slides, yes. We can go back to the slides, day 3. Day 2, day 3. Why is day 3? This is day 3. Oh, here we are, exactly, great. This is the diamond. Look what he's doing. He do like this reduction. Look here. He actually identify x2 and x6. He identified these two. Okay? And then remove this, doesn't care for them. And so instead of this, when he identified these two, he will have this situation. He will remove V, W, and Z. No, he actually identify all this into a with X4. Yes, when he identified these two, okay, what's exactly what he's doing? Sorry? He identified these two, but what happens with VWZ? Maybe he identified these two together. So if I contract these two, okay, I mean actually you can say he contract all this into a vertex. Okay, contract, this is new vertex X star. Contract into a vertex. Look, X star, okay. And by induction he colored this graph. And then he go back. Okay? So, maybe he get here color, let's say, I don't know how he use colors to be the same, doesn't matter. Maybe he use here color 1, okay? We can assume here is color 2 and here is color 3, okay? We don't know for x1 and x5, okay? And now, when we go back, we're gonna have here color 1, color 1 and color 1, okay? And we're gonna have here color 2 and color 3. Now for x1 and x5 here we have several possibilities, yes? We have several possibilities for x1 and x5. x1 can be colored like 2, 3 or 4, yes? 2, 3 or 4. Let's say first case 1, x5 can be colored two possibility. Here can be 2, 3, and 4, and here can be 2 and 4. So we have 6 possibility. And I put the values of others one, U, V, W, and Z. Let's say x1 is colored 2 and x5 is colored 2. So we have here 2, 2. If we have here 2, 2, maybe we can color it here 4, and we can color it here 4, and we can color it here 3, and we can color it here 3.
3.
Aha! So what should we color it? Maybe we can color it dimensional before here. Maybe we can color it here 1. Okay? And you can be colored with 3, okay? And we can be colored with what? Z. Yeah. 4. You want 4. Okay. 4. And they get further, yeah. No, you want to color this is what you want probably So you have here 3 and 4, yes, available colors. You have here, no, 1 and 2, 3, 1 and 4. You have here 1 and 2, you have here 3 and 4. You have here 3 and 4, and you have here 1 and 2, 3 and 4. So you want to color this one by 1. No, but this is a problem. Oh, this is a problem. You cannot color this part. 3, 4, 3, 4. What they do? He identify x2 and x6. This is the hardest case. Aha. This is the hardest case actually. Everything else is easier. x2, he goes like this. We may assume that x2 and x6 are 1 and x4 is 3. He assumed like that. x4 is 3. He assumed this. Okay? So x3 is adjacent to x2 and x4. We may assume x3 has color 2. He assumed this is also has color 2. This x3 has color 2. So we have only here and here, yes, values. And he says everything is simple, everything will go smoothly, except x1 is 2. The only hard case, this is 2. x3 is okay 2, and x5 is 2. This is the only difficult case, he says. We may check later, or you will check later. Okay. And now he said, we claim that x1, x3, and x5 belong to same Hempel chain H24. And he said, if x1 is not in the same component as x3 and in the same component x5, then recover x1 by 4. Using Kemper chain. He will make a Kemper chain here, yes? Okay. And set Cu to be 2, Cv to be 3, Cw to be 4, and Cz to be 1. And this works. So he's trying here Kemper chain, yes? This is like with with computer, yes? Otherwise, if not, now x1 and x5, otherwise without rules of generality, we assume that x are in the same component distant from one of x3. So we have here component 2, 4, 2, 4, and distinct from the one of x3. Then again, using Kemper chain, we recover x3 by 4, and then he create new coloring here. This is, I think now is 2 here, yes, and then 4, and then he extended to Cu is 4, 4, Cv is 2, Cw is 3, and Cz is 1. He do like this, and then get coloring again. And finally, if x1, x3, x5 belong to the same component 2, 4, probably we're gonna have something like this. and this is 2. This is 2. Okay, we're gonna have here 2, 4, 2, 4. This is ugly. We're gonna have here 2, 4, 2, 4, 2, 4, 2, 4, and here 4, 2, 4, 2, 4, 2, and 2, 4, 2, 4, 2, 4, and so on. We're gonna have like this. Now he said apply H13, 1 and 3 Kempe chain to recover X2. Okay. He said X2 to recover 1 and 3. It cannot, this Kempe chain cannot go like this to this vertex, yes. To which one? To this one, yes. It can instead, it can stay only here inside, okay? And then we can put here color 3. And then we can extend it. Cu will be now 4, Cv will be 1, Cw will be 3, and Cz will be 4. So this is how you do it. And at the beginning we jump few cases saying this is trivial, yes, other cases. So this way we prove it now that Birkhoff diamond is a C-reducible. So we smartly identify something, and whatever we get, we will be able either trivially to solve it or to use Kempe chain. We have this one case very complicated. We use twice Kempe chain or 3 times, yes. And imagine diamond is small configuration with 4 vertices, Birkhoff diamond. Birkhoff diamond originally is this, 5, this is Birkhoff diamond. And we have 5, 5, 5, 5, 5. Now imagine you have some 10 vertices. And then you will have plenty of colorings. Now this coloring you have to sometimes to apply Kempe chain. Is it possible here Kempe chain, or is not doesn't exist Kempe chain there? And then you use a lot of computer power. Okay. Anybody want to solve some other problem? Five zero two. So what is the best? Let's see the best what says. Yeah. So, exercise 12, if you think. 3 connected, so 3 we have he said every 3 connected graph contain one of the configurations here is face of size 5 or less, and here is a vertex of degree 3. 4 vertex incident with triangle. And 5 vertex. So how you should prove this? We should take some initial charge. We would like to make contradiction, assuming that we don't have these three things. We take initial charge, we redistribute it smartly, and at the end we get positive, yes. So maybe what should be initial charge? What do you prefer? What do you think is a good idea? Oops. What do you think is a good idea? I move it a little bit like here. What should we take initial charge? Can somebody help me? Should we take this? D minus 6 plus 3L minus 6, 2L minus 6, 2L minus 6 equal to minus 12. So total charge will be, so every vertex has initial charge this. And every face will have initial charge. Okay. So look, if I have three vertex is very poor. But if I exclude this 5 minus, 3 vertex is not adjacent to 5 minus. So what does mean? That means like 6 plus vertex will send how much? 1. This will be my first rule. 6 plus face sends 1 to incident 3 vertex. Okay. R2. For face, you have charge how much? 2L minus 6, yes. L4, yes, it is going to have, this is not, doesn't exist. So for face, for vertex, 4 vertex is deficit. Look, around 4 I will have only 4 faces or more. I will set 1/2. So second rule will be 4 plus face sends 1/2 to a 4 vertex. Okay, this is my second. And third rule, it will be about 5 vertices. Look, we don't have this. We don't have 5 vertices with adjacent 4. So we can have 5 vertices with adjacent only 3 triangles. So 5 vertices will have at least 2 faces which are not triangles. So we're going to have again the same rule onto a 5 vertex. 4 or more face will send 1/2 to a 5 vertex. So do we have now with this, let's see what happened after we apply these 3, this is the same, yeah, 2 rules, yes. Okay, 3 vertex, initial charge, final charge of a 3 vertex. At the beginning it was -3, okay, but it gets by rule R1 3 times 1. You know, when we have a 3 vertex, this is a 6 face of more, 6 face of more, 6 face of more, and each one sent 1. So it will be at least exactly 0. 4 vertex. 4th vertex is by this, we excluded this because we're going by contradiction. 4 vertex have initial charge -2, but we send it to it because it has no triangles, only 4 faces and more, by rule R2, 4 times 1/2, and this is 0. 5 vertex. Final charge is -1, and it has, because this is forbidden to have 4 triangles and 5 triangles, it has at most 3 triangles. That means at least 2 4 plus faces, so it will be like 2 plus 1/2, it will be at least, here will be at least, it will be at least 0. 6 vertices and more, 6 plus vertices, we have final charge is the same like initial charge, nothing happened, it is strictly bigger than 0. It will be like d degree -6, which is like at least 0, yes. This is for vertices. Rule 2. If I have here 4 or 5 vertices, and here if I have a face 4 plus 4 or 5 or 6 and so on, then this face sent to this vertex 1/2. Why? Because we create the rules. It is good idea to send it, to prove this.
What is the relationship between what the comparison in this?
So I want to make my 4 vertex positive or non-negative, the same with 5 vertex. And if this is forbidden, 4 vertex is for not with triangles. What does mean? All faces around the 4 vertex are of degree of size at least 4. Then I say, okay, I need 2. 4 faces, and I need total charge 2. So let's each of them send 1/2. And then I make the 4 vertex non-negative. The same here. This configuration tells that around 5 vertices I will have 2 faces which are of size at least 4. Let's these 2 faces send each 1/2. Then I get 1 for 5 vertices. At least 1 I get extra. But initial charge was -1 plus 1 is 0. Great. So why I have such rules? Rule R2, because it worked perfectly. Magically. Okay. And then now we have to check the faces. 3 faces do nothing. It's okay. 4 faces can send how much charge? To each vertex sends at most 1/2. It had initially 2, minus 4 times 1/2, it will be at least 0. So what should 5? What is next? 5 phase. Let's check also 5 phase, and then we do something in general. How I put a new page. Let's check it. No, I'm on wrong place. No. Maybe here. I don't know why it's put it before or after. So what if you have 5 phase? Look, if we have 5 phase, it can send to each of them 1/2. Is this okay? I don't know if it is okay. So we have initial charge 2 multiply 5 minus 6. It's 4 initial charge. And it can send 5 over 2. So initial charge minus the charge sent it, this will be strictly positive. So 5 phase will stay positive. 6 phase and so on. Let's do it in general. Let's do in general. Let's say like this. Initial of phase is of size, I think 4 or 5, let's assume, and this will be like 2d minus 6 minus, I sent 1/2. No, I should be careful. No, it should be done separately. This should be now at least 6. At least 6. Because 6 vertex may send 1 to 3 vertex, yes? So we should do separately. And this is like final charge of a 6 phase or more will be like this. At least 2d minus 6 initial charge, no, without this. Because it has length d, it has d vertices. In the worst case, to each of these vertices sends 1, we get d minus 6, but this is bigger than or equals to 0 because d is at least 6. That's it. Maybe one of other days we prove also Kotzing theorem. Kotzing theorem. The other one, the question 11 could be one of the next days. We will see if we have time. We didn't prove today snarks. Peterson is the smallest snark. We leave it for some other day. We like it too much discharging, so that's it, yes? We have done for today. Tomorrow 9 o'clock. Tomorrow we will do a little bit less knowledge. And something that we didn't manage today. We didn't manage today. So always have something that we didn't do. Some hard-figure conjecture, yes, to mention. Maybe some graph on surfaces, and this is like question related to this question 9, 8, also related, 10 question related, and 15 and 16, the question related with something we didn't manage to speak to them. You simply go slower, back again. Okay. 5 phase. Let's check also 5 phase, and then we do something in general. How I put a new page. Let's check it. No, I'm on wrong place. No. Maybe here. I don't know why it's put it before or after. So what if you have 5 phase? Look, if we have 5 phase, it can send to each of them 1/2. Is this okay? I don't know if it is okay. So we have initial charge 2 multiply 5 minus 6. It's 4 initial charge. And it can send 5 over 2. So initial charge minus the charge sent it, this will be strictly positive. So 5 phase will stay positive. 6 phase, and so on. Let's do it in general. Let's do in general. Let's say like this. Initial of phase is of size, I think 4 or 5, let's assume, and this will be like 2d minus 6 minus, I sent 1/2. No, I should be careful. No, it should be done separately. This should be now at least 6. At least 6. Because 6 vertex may say 1 to 3 vertex, yes? So we should do separately. And this is like final charge of a 6 phase or more will be like this. At least 2d minus 6 initial charge, no, without this. Because it has length d, it has d vertices. In the worst case, to each of these vertices sends 1, we get d minus 6, but this is bigger than or equals to 0 because d is at least 6. That's it. Maybe one of other days we prove also Kotzing theorem. Kotzing theorem. The other one, the question 11 could be one of the next days. Yeah, we will see if we have time. We didn't prove today snarks. Peterson is the smallest snark. We leave it for some other day. We like it too much discharging, so that's it. Yes. We have to wait tomorrow 9 o'clock. Tomorrow we will do a little bit less knowledge. And something that we didn't manage today. So always there's something that we didn't do previously. Some hard-degree college conjecture, yes, to mention maybe some graph on surfaces, and this is like question related to this question 9, 8, also related, 10 question related, and 15 and 16, the question related with something we didn't manage to speak today. If simply go slower, try to get it. Okay.